In this set of notes, we're going to be looking at the key questions: what do waves transfer? What are properties of waves? What are the two types of waves? And what are the parts of waves? What is a wave? And what are properties of waves? Well, a wave is a transfer of energy without the transfer of matter. So it's energy moving from place to place. Matter involved in waves does not move. Only the energy moves from one place to another. All waves, though, have speed, frequency, wavelength, and amplitude. What are the two types of waves? There are longitudinal and transverse waves. Longitudinal waves are called compression waves because parts of it get compressed together and pushed together. Sound and seismic waves are examples of longitudinal waves, and light is an example of a transverse wave. If you're looking at an example of a longitudinal wave, longitudinal waves or compression waves will move the energy with that compression, but matter is not moved. If you look at the red dots in these animations, you know they just move back and forth, but they don't move down with the wave. This is an example of a transverse wave. Notice that instead of going back and forth or parallel like a longitudinal wave, the transverse wave goes up and down or perpendicular to the medium. And again, the particles don't move, it's just the energy that is moving. What are the types of waves? Well, we have the two different kinds of waves, and we have different parts for each one. The longitudinal wave has compressions where it's pushed close together, and rarefactions, where the parts are spread farther apart. For a transverse wave, which goes up and down, we have a trough, a crest at the top, the wavelength, which is the distance between two corresponding parts of a wave, and the amplitude, which is the distance from the level or equilibrium point of the wave, it's also called the normal, to the top, the crest, or the trough, the bottom. Those are the parts of the transverse wave. Let's take a look at the properties of waves. Let's start with the wavelength. Wavelength is the distance between any two corresponding parts of a wave. So from crest to crest or from trough to trough, that is the wavelength. And if we decrease the wavelength, that distance gets shorter. If we increase the wavelength, that distance gets greater. And you notice particularly if we make a really small wavelength, those crests get really close together, as do the troughs. Now let's take a look at amplitude. The amplitude is how far up or down the wave crest or trough is from the equilibrium or resting position. And we can increase our amplitude to make that wave taller, or we can decrease the amplitude and that'll flatten it out. Frequency is how often a part of the wave crosses a point in a certain amount of time. So if we have a lot of crests crossing a certain point in a certain amount of time, we have an increase in frequency. It's happening more often. If we decrease our frequency, the crests pass a certain point less often. There are several properties of light, and there's also properties of sound, two different kinds of waves. We want to be able to tell the difference and compare these two types of waves. Light waves travel extremely fast, much faster than sound, and they do not need a medium to travel through, so they can travel through the emptiness or vacuum of space. All the range of light types is contained in what's called the electromagnetic spectrum. And light, when it hits matter, can either be reflected, absorbed, refracted, or transmitted. Also, light exists two ways at the same time, both as a particle, a photon, and as a wave. This is the electromagnetic spectrum, and light waves go from extremely long wavelengths to very short wavelength, and they have very low energies at one end and very high energies at the other, and these enable different parts of the electromagnetic spectrum to have different properties and different uses for us. Light can also reflect, and it can refract, and you should know the difference between those two. Reflection is the bouncing of light, refraction is the bending of light. Sound requires a medium to travel. There is no sound in space. The speed of sound will depend upon the density, elasticity, and temperature of what it's traveling through, so it travels faster through solids. And sound is produced by vibrations. And loudness is measured in decibels, and frequency is what we also call pitch. The Doppler effect can be seen in both kinds of waves, light and sound, but we're more accustomed to seeing it in sound waves. And this is a change of frequency as something comes towards us. Those wavelengths are closer and a higher frequency, and it goes away from us. It has a longer wavelength and a lower frequency. So this is what it looks like with the Doppler effect. Something's coming towards us, they get squished up. We have a high frequency, behind us, low frequency.
Hopefully you heard a high frequency as the fire engine came towards us, low as it went away from us. That is the Doppler effect. And that's the notes for waves.